Hey, on this nice chilly Sunday, I'm going to give a recap of a couple of problems that I interacted with in a couple of the math subreddits. It's always fun to see what time of the semester it is by the activity on these subreddits because lots of people are studying pretty much the same thing at about the same time, and so these problem themes start to come in clumps. And so what I've done here is picked one problem having to do with a line integral in scalar form. So this is multivariable calculus, like Calc 3 for most people, and one involving a line integral in vector form. We'll take a look at each. Also, my dog just stopped barking right before I clicked record. Hasn't made a peep all day. As soon as I'm ready to start recording, bark, 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 bark. But she did quiet down, so hopefully she will remain quiet. So here comes example number one, multivariable calculus, a line integral with only scalar information, regular old scalar function, no vectors in sight. Okay, so we're going to evaluate the line integral or the contour integral of the function xy squared z on a contour which is floating in space up at z equals 4 and is the intersection of that plane with the garden variety paraboloid z equals x squared plus y squared, further with the restriction that we're only going to consider y points whose y coordinates are greater than or equal to 1. So you got this paraboloid opening upwards, you got the plane z equals 4, those two surfaces intersect where the recipes are equal, where x squared plus y squared equals 4. That's a circle of radius 2, except now it's floating in three-dimensional space up at z equals 4. But then, like I said, we're also restricting y to being greater than or equal to 1. So here is a badly drawn version of this picture. One of the reasons I like multivariable calculus is that you get to play around in three-dimensional space. The drawback is that you have to draw things in three-dimensional space. So the blue shape is the paraboloid, and then up here at z equals 4, we've got the intersection of the plane z equals 4 with that paraboloid, and so we trace out this circle, x squared plus y squared equals 4. Okay, and now I'm going to kind of flip that down so I'm looking at it almost from overhead so that we can see what it means to restrict the y coordinates to be greater than or equal to 1. So we take what was that full circle, and I haven't even bothered drawing the quote-unquote lower half. So this is now looking down on that circle so that we can see the x and y directions, and I've tried to illustrate that we're going to start our contour at a y coordinate of 1 and take all the points on the circle above those markers. Okay, so this blue shaded arc of the circle is our contour of interest. Now, to evaluate this line integral, we need to parameterize everything, right? So the story here is in Calc 1, you learned how to do single integrals. Calc 3, you eventually learned how to do double integrals, triple integrals, and then you start getting these line integrals and surface integrals. But what we do with those is we just return them to being garden variety single, double, or sometimes triple integrals, because those are the things that we know how to evaluate. And so in most cases, we can do that through parameterization. Okay, so how do we parameterize a full circle? Well, it's x equals r cosine t, y equals r sine t. Here, the radius is 2. The full circle would go from 0 to 2 pi. Now, why are we not going to use 0 to 2 pi here? Well, again, that's because we're not using the full circle. We're only using this blue arc. So we have to know, see a little question mark right there, what is the starting value of the angle that puts us into this contour, and we then travel around the contour, and then we leave it on the opposite side of the circle with the same reference angle. Okay, so this is the picture that sort of describes that. So the dashed line, the dashed arc is the remnants of that circle. And so if we're going to describe this arc by providing the parameter or the angle that locates any particular point, we begin right here at y equals 1, but remember the radius of this circle was 2. And so we can finish this circle if we need to with the length of that mystery side, but we actually don't need it. This angle that puts us into the place where our contour sits is pi over 6. It's the inverse sine of 1 over 2. And so on the opposite side, the exiting angle, as we sweep around reverse of a clock, counterclockwise, we leave our region or our contour at 5 pi over 6. Okay, so this blue arc begins at theta equals pi over 6, and we leave it, we finish it at 5 pi over 6. So those are the parametric equations that describe this contour for us. And then our job is to take everything that we're dealing with and put it in terms of that contour's parametrics. So again, repeating what the contour is. Whoops, I forgot to edit this. This should be pi over 6 to 5 pi over 6. I'm not going to go back and fix it now. But the function that's being integrated, x, y squared, z, we put in the recipe for x, we put in the recipe for y, and we put in the recipe for z, and then shake it all out, and we end up with 32 sine squared t cosine t. Now, let me go back to where did I put it this far back? Okay, so we're building this contour integral. What do we do with ds? We don't know. That's why we're turning everything into parametrics. We have to convert this into a regular garden variety single integral. It's just the process bloats the thing that we're integrating. So we've turned x and y squared and z into their parametric form. Now, what do we do about this ds? Well, we have to turn it into something to do with dt. The secret to that is memorable from like an arc length type of calculation, which you learn before you learn how to do all these line integrals, but it's a stepping stone to get here. ds is given by the square root of x prime squared plus y prime squared plus z prime squared, where x, y, and z are the coordinate recipes for the curve. So again, here they are, 2 cosine t, 2 sine t, and 4. So we find each of those derivatives, and then we load all that stuff up into this terrible square root, but it shakes down pretty nicely because we just end up with the square root of 4, because sine squared plus cosine squared is 1, so factor off the 4, etc., and this just becomes 2 dt. Okay, so all together now, xy squared z looks like this. ds turns out to be 2 dt, and so this contour integral involving x and y and z and s, everything is now in terms of t, and by golly, I forgot to update these limits of integration from pi over 6 to 5 pi over 6. Again, I'm not going to go back and fix that. When I originally read the problem, my brain interpreted y greater than 1 to being y greater than 0. So I originally did the problem with 0 and pi as limits. Okay, but should be pi over 6, 5 pi over 6. However, it actually makes no difference. Okay, to do this integral by hand, we would have to do a substitution like u equals sine t. It wouldn't be hard. Oh, look, I put them back on. It's been a long weekend. Okay, so the limits are now correct on this integral, and the net result is 0. And we have done all that work for literally nothing. Okay, now, is an answer of 0 a bad thing? And I want to emphasize this. That's one of the reasons I like this problem, because when I was teaching, it was very common for students to come to me and say, I just did this triple integral, and I got 0, and I know that can't be right, because aren't I calculating a volume or something? Or a double integral, I got an answer of 0. Aren't I calculating some kind of area? And the answer is not necessarily. Getting an answer of 0 in these contexts is not necessarily a bad thing. So think about the fact that what you're doing with this contour integral is you're like the little calculus ant, and you're walking around that circular arc. And at every point on that circular arc, you're picking up values of the function xy squared z, and you're accumulating all the values of that function. Now, if we go back and look at this blue arc, okay, remember the function is x times y squared times z. So y is always positive, z is always 4 for this case, And for every positive x, where here we would calculate x, y squared, z with that positive x coordinate, there is a mirror image of that point over here where we're calculating x, y squared, z with the negative x. And so every contribution to the integral from the right half of this arc has a canceling contribution to this other half, from this other half. And so, no, it actually is not bad to get a result of 0. It's actually kind of nice. And you know this already from Calc 1, the integral of sine of x from 0 to pi over 2. The integral of sine of x from 0 to 2 pi is 0, right? It wasn't a problem then because every positive value of that function was counterbalanced by a negative value. The exact same thing is happening here. So we could have actually done this problem, and having gone into it before we did a single calculation, we could have predicted that we would get a value of 0 just because we could look at x, y squared, z, look at the contour that we're accumulating values of that function over, and noticing that positive negative symmetry because of the values of x. You can do the same thing with double and triple integrals, and I need to make a video that tells that story. Try to put that in my mental to-do list. Okay, but there we go. The answer is 0, and that's fine. In fact, it's kind of cool. So now let's switch over to a vector version of a line integral. The question was not quite phrased this way, but I'm interpreting it. I left something off that we'll get to in a second. Here's a vector function, 2x plus y squared plus 3x squared y, vector field. The first and second components of this, I just read the first one, but forget it. I'm not even going to try to read them off. They're nasty, right? And we're going to find the contour integral of f dot dr, where c is the arc of the curve matching y equals x sine x from 0, 0 to pi 0. First of all, this is what's known as a work integral. If this force is a work-doing force, we are calculating the work done by that force moving an object over this contour. Now, I don't have it prepared in advance, but y equals x times sine of x sort of looks like this, where that's 0, 0, and this is pi 0. So we're sort of going in that direction. So the force is moving an object along this curve. What's the work done by that force? That's the equivalent version of this problem. Now, with a vector contour integral like this, there's the easy way out, and there's the, oh no, we have to do it the long way version. Let's check the easy way out first. If the vector function is conservative, then we have an easy way out. Easy in quotes because it might not be that easy, but it's easier than the alternative. Okay? We test to see if a vector field is conservative by looking at its curl. Now, this vector field only has 2 components. So how do we do its curl? Well, we just slap in a third component of 0 and do the curl that way. And so we would open up the curl operator on this and see if we got 0 back, right? The second way to do it for a 2-dimensional vector field, the equivalent of looking for the curl being 0, is to just name each of these components big P and big Q and see if the sort of crisscross derivatives, the derivative of P with respect to Y and the derivative of Q with respect to 0, are those things equal? If they are, then it's conservative. Now, for this particular vector field, the derivative of that first component with respect to y is 2y plus 3x squared. The derivative of this second component with respect to x is 2y plus 3x squared. Ta-da, they are the same, so this thing is conservative, and so we do have the easy way out of this problem, which is to apply the fundamental theorem of line integrals. This requires finding a potential function for this vector field. Now, don't panic, because this is just a souped up version of a regular old fundamental theorem of calculus problem. How do you find the integral of a function? You find its antiderivative. So you kind of step up a level from the original function to its antiderivative, plug in the endpoints of integration, and subtract. The exact same thing is going to happen here. We're going to go from this vector field, which is conservative. So it's going to have this thing called a potential function. And then what we're going to do is evaluate this potential function at the endpoints of the contour and then subtract, right? It's the same overall process. What is the potential function? Well, we have a vector field sitting there, and we need to find a scalar function whose x derivative is the first component and whose y derivative is the second component. The gradient of the potential function is the vector field we're looking for. So whatever mystery scalar function we're looking for as the potential function, its x derivative needs to be that, 2x plus y squared plus 3xy. And from that, we can immediately determine that at worst, this scalar potential function is going to be x squared plus xy squared plus x cubed y, because remember, each of those individual terms are a derivative with respect to x of a term from the potential function. But then that function could also have any other function of y that we want, because the derivative with respect to x of any function of y is going to be 0. So no matter what sits here, if we take this function and take its derivative with respect to x, we will get that component. Okay, this is the scaled up version of the arbitrary constant plus c. Now, how do we figure that out? Well, then we go over to this other component, and remember that whatever potential function we have, this component had better be its derivative with respect to y. Okay, so we know just from looking at this component, that has to be the derivative with respect to y of this mystery function we're trying to find. But we have an 80% complete version of this potential function, and its derivative with respect to y looks like this. From, derivative with respect to y of that, 0. With respect to y of this, 2xy. Derivative with respect to y of this, x cubed. Derivative with respect to y of this, I don't know, it's g prime. Okay, but now we have two representations of what this derivative with respect to y needs to look like. It has to look like this version from the vector field itself. It has to look like this based on our building template of this function. And so this g prime has to be the thing that becomes the 3y squared. So what function's derivative becomes 3y squared? Well, y cubed. Okay, so that's what the mystery value is, or the mystery function. We could throw on an extra constant, just like in Calc 1, but we will assume it's 0, because we'd get the same answer even if we put in like 75 for that constant. So, potential function for this vector field, x squared plus xy squared plus x cubed y plus y cubed. Whew. Okay, now remember that our contour was this thing, x times sine of x from 0, 0 to pi 0. All we got to do now is take this potential function, plug in 0, 0, we get 0. Plug in pi 0, we'll get pi squared and 0 and 0 and 0. So pi squared, take the difference, and ta-da, the answer to this contour integral is pi squared. Not bad for a few minutes work. Okay, now what if we weren't lucky and maybe that vector field wasn't conservative? What would we have to do? Well, just like in the other problem, which is why these two go nicely together, we would have to parameterize everything and just build that integral from the inside out using the parametrics, and then evaluate it as a good old-fashioned single integral with respect to the parameter. Okay, so how do we parameterize our contour? It's just a function y equals f of x. How do you parameterize that? Well, you just make x the parameter and then write down what y would look like given that parameter. There you go. And how do we know the endpoints of that parameter? Well, you just take the first and last x values you're going to use. So there we go. There's the parametric representation of our vector function which describes the contour. Since we're integrating f dot dr, we better see what dr looks like, right? So the derivative of t is 1, and the derivative of t sine t is a little quickie product rule, and it turns into this. Now, the vector function was horrendous, and I'm sorry that this is all bleeding over on top of my little logo there, but you're not going to sit here and look at all those details anyway. If you're going to do that, you're going to have to pause this And so then you would have time to look at the overlap between this mess and my little logo. But we'd have to take x is t and y equals t sine t and load up every single term in this vector function with its parametric representation. And then we would have to do the dot product of f dot dr with all of this garbage, and then integrate that from 0 to pi. You want to do it? I don't want to do it. We could do it, right? This is f dot dr all blown out into a single function of t. We would have to integrate from 0 to pi. Once we're done, it better be pi squared, because that's the answer we already know about from the easier version of this problem. But we could do it with parametrics. I don't want to, so I'm done. I hope that helped understanding of these two scenarios a little bit. Let me know if you don't. Visit metalprofessor.com. Yeah, drop me an email there. And enjoy. Thanks for watching.